Cool. All right, let's get started here. We're going to pick up where we left off last time. Last time we were discussing how aldehydes and ketones will react with nucleophiles, what's called a nucleophilic addition reaction, where that nucleophile is going to attack that electrophilic carbonyl carbon. Okay? Our carbonyl oxygen doesn't go anywhere, so we get a hydroxide group with our nucleophile attached to what was formerly our carbonyl carbon. Okay? If we use a basic nucleophile with this negative charge, we're going to need to protonate that oxygen. And so what we're going to use as our proton donor is just going to be the protonated form of that nucleophile. So let's start off with a specific example here. All right. Let's take 3-pentanone. We're going to react that with some cyanide ions. And we're going to use hydrogen cyanide as our proton donor. All right, I want you to take a second, see if you can't first give me the product of this reaction, and then give me the full mechanism of this reaction as well. All right, so in this cyanide ion here, which one of these is actually my nucleophilic site, the carbon or the nitrogen? Yeah, the thing actually holding that negative charge is that carbon. If I'm going to draw out the full Lewis structure here, this is a carbon-nitrogen triple bond. Carbanions are pretty freaking unstable, but having it bound triple bonded to this nitrogen, it's resonance stabilized. So these things are one of our few carbon nucleophiles here. If I'm going to just draw my product, which is always a good place to start for your mechanism so you know where you're going, I have what used to be my carbonyl carbon. That carbonyl oxygen is now a hydroxyl group. All right, and now I'm going to draw my carbon nitrogen. I'm going to draw the actual bond line structure here. Boom. All right, I have my new carbon-carbon bond. To be clear, right, my carbon in my cyanide ion is located here in my molecule, right, at the base of that triple bond. If I'm going to do my mechanism, I'm going to show my nucleophile attacking that electrophilic carbonyl carbon. That carbon's a good electrophile because it's in that bond with that oxygen that's pulling electron density away from it, but also importantly because we can kick that pair of electrons up onto that oxygen and we never break that octet of that carbon. Okay, so now I have my nucleophile attached, but if I follow my electron pushing arrows correctly, my oxygen now has that net negative charge. All right, so in order to finish this mechanism here, I'm going to need to protonate it using the hydrogen cyanide. It's going to attack that, and look at that, we replenished our supply of cyanide ions in this reaction. Cool, okay. So, we're going to talk about this product here for a second. I have no idea why they chose this chapter to introduce these, but these are nitriles. Any organic compound that has that carbon-nitrogen triple bond is a nitrile. Our functional group here, this is a nitrile. You'll hear this group referred to as a cyano group. So kind of like how alcohols contain hydroxyl groups, nitriles contain cyano groups. All right, and so two sort of random reactions of nitriles that are placed in this chapter is one, we can reduce them using one of our common reducing agents, lithium aluminum hydride, followed by that acidic workup. All right, remember when we were reducing our aldehydes and ketones, we're adding a bunch of new carbon-hydrogen bonds. And we're going to do the same thing here. This will reduce adding a bunch of hydrogens onto either side to an amine. All right, real careful. How many carbons should be in that amine that I'm going to draw? 4, right? So remember, everybody always forgets. Don't forget to count the carbon at the base of that triple bond. There are 4 carbons in that nitrile. All right. It turns out that these nitriles are actually fairly easy to oxidize as well. We just need some acid and heat. All right, kind of counterintuitively, our oxidation product, it will actually lose that nitrogen in the process here and will create a carboxylic acid. Okay, so just to practice these reactions, let's take this nitrile that we just created from our aldehyde. And we're going to perform these 2 reactions. And I want everybody to take a second and give me the product of these 2 reactions here. I will just caution to be extra special sure to count your carbons in these reactions here. so importantly, when I do these reactions, when I do that nucleophilic addition to my aldehyde, in this case my ketone, I add an extra carbon on there, right? That cyanide ion is bringing an additional carbon with it. So now I'm going to reduce that to an amine. But again, I have one additional carbon compared to my ketone that I started with. I colored it in orange here. Likewise, if I'm going to instead do that oxidation, I'm going to convert that into a carboxylic acid. Kind of crowded in here. All right, and again, that occurs on that extra carbon that I added in that nucleophilic addition reaction. Okay, so again, honestly, it's kind of out of place. We'll talk about nitriles in our carboxylic acid derivatives chapter. They put this here in this chapter, and I've kind of labeled this under the category of other reactions of aldehydes and ketones that we got to know here. If we do a nucleophilic addition and add that cyano group on there, we can either reduce it with lithium aluminum hydride to an amine or oxidize it using acid and heat to a carboxylic acid. Cool. All right, now in all of these nucleophilic addition reactions, we looked at a bunch of different nucleophiles, and one atom that was notably absent that we've seen play the role of a nucleophile before was nitrogens, all right? And I said that's because we're going to kind of save them and put them in their own category here of nitrogen nucleophiles. All right, so first of all, we got to put them in a separate category in our brain because quite frankly, they're kind of a pain in the ass, all right? First of all, the products that we get are a little bit different looking than what we would expect based on our normal just scheme of nucleophilic addition that we've been doing up until this point. So let's take a sample here. Let's just use a simple ketone like acetone. All right, if we react acetone with a primary amine, meaning that that nitrogen is bound to just one carbon atom. All right. This produces what's not an amine, but what's called an imine, where that carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. All right, so if we look up here, it's like I've taken my amine here and I've just put that, boom, attached that nitrogen to where that oxygen used to be, right? I used to have a carbon-oxygen double bond. Now I have a carbon-nitrogen double bond, all right? So in order to do that, that nitrogen had to lose two of those hydrogens in that process, right? The two that it were originally bound to. Well, if instead I take a secondary amine, a secondary amine is when that nitrogen is bound to not one, but two carbon atoms. Okay, well now I can't form an imine. I can't make a carbon-nitrogen double bond because I only have one hydrogen. Okay. So I'm going to have just a carbon-nitrogen single bond. But wait, there's more. It turns out that we still lose an additional hydrogen here, but it's from the neighboring carbon, forming what's called an enamine. So first of all, our nitrogen nucleophiles, we're going to put them in a kind of a separate category in our brains because they don't behave like all of our other nucleophiles where we quite simply just attach them to our carbonyl carbon. We got a little extra consideration here. Our primary amine will form a carbon-nitrogen double bond, a functional group we call an imine. And if we used a secondary amine where there are two carbons, we're going to form an enamine, where we have a carbon-nitrogen single bond, but then we have a double bond that's formed on our neighboring carbon. Okay? Cool. So, the other reason why we want to put these into a separate category in our brains is previously we had divided the world of nucleophiles up into acidic nucleophiles and basic nucleophiles. All right? Nitrogen is going to be what's considered a neutral nucleophile. Or we're going to rather use neutral conditions for our mechanism. All right, now we're going to call them neutral conditions, our mechanisms that we have like this separate category in our brain. All right. Importantly, under basic conditions, we said we shouldn't see any positive charges because we can't have any strong acids. And under acidic conditions, it was the opposite. We can't have any strong bases, so we shouldn't see any negative charges unless they're halogens. Under neutral conditions, we're allowed to have everything. Allowed positive and negative charges. We're going to see them both. All right. Now, truthfully, these aren't pH 7 neutral conditions that these reactions are carried out at. It turns out that they're most optimal around pH like 5 or 6. So we are slightly acidic, but nowhere near like our HCl or sulfuric acid bomb that we would put in for our typical acidic conditions. Okay? Nonetheless, we're going to need to have our acids, our proton donors. All right, and since this is slightly acidic conditions, we're going to use hydronium. All right, and I guess let me just put, we're going to say truthfully, slightly acidic. So for acids, for our proton donors, we'll use hydronium. And then what do we think we'll use for our bases? And our H plus acceptors. At that pH of 5, we're still using it in that slightly acidic region. So we're not going to have any hydroxide. We're going to use water. All right, so again, we got our nitrogen nucleophiles, and we got two reasons why we're going to put this in a special category in our mind. It's got this little asterisk next to it because it's kind of a pain in the butt. Number one, the products aren't as simple as what we would expect based on all the other nucleophiles that we've been using, right? We got these weird imines and enamine businesses going on here, all right? and 2, because of our mechanism conditions. We got this new category of our mechanism conditions, which we call neutral conditions, where both positive and negative charges are going to be allowed. Cool. All right, so let's do our primary amines first. Creating what we call that enamine. All right, this is going to be kind of the most intricate mechanism that we've seen to date, so we're going to kind of use it as an exercise to try to practice drawing mechanisms here. What's up?
Wasn't the primary amine the imine?
Yeah, sorry. Got a lot of enes going on here. Making sure we're paying attention. Okay. Cool. So basically, like, I'm going to put in some arrows. I want you to draw the next step in the mechanism, or I'm going to draw the intermediate, and I want you to fill in the arrows here. Okay? And by the end, we'll have our complete mechanism of this reaction. All right, we're going to use just the simplest primary amine that we can, which technically is not even an amine because there's no carbon, but we're going to use ammonia here. All right, cool. So everything kind of starts out like we would expect here. We have our nitrogen nucleophile. It's going to attack that electrophilic carbonyl carbon. And that electrophilic carbonyl carbon is so good at accepting electrons because that can bump that pair up onto that oxygen. All right, so fill in my missing intermediate here that we need for this first step following these electron pushing arrows. All right, so my oxygen's accepted that pair of electrons. So now it's got 3 lone pairs, which means it's got a negative charge. My nitrogen now continues to have those 3 hydrogens bound to it. And since it's got no lone pairs and 4 bonds, what should be the formal charge on that nitrogen? Positive. So here we see we already got an intermediate that would have broken all of our rules under acidic and basic conditions, right? So here's our neutral conditions intermediate here that has both a positive charge and a negative charge, all in the same species. And you're looking at this thing being like, well, that looks weird as heck. Yeah, well, one of those groups is a good base, the negatively charged oxygen. The other one is a good acid, that positively charged nitrogen. So the next step in this mechanism here is going to be to kind of rectify that situation. We'll get a neutral OH group and a neutral amine group. And you're going to take a second and fill in my missing electron pushing arrows that takes me from A to B here. Right, so I need that pair of electrons on that oxygen to reach out and grab that hydrogen, and then I got to break that hydrogen-nitrogen bond and deliver that pair of electrons, and I should have been good and put these in over here so we could see more clearly, and deliver that pair of electrons to that nitrogen atom. Okay? Now, truthfully, in our textbook, you'll see this broken up into two separate steps. You'll have water accept this proton here, and then in a second step, you'll have hydronium give a proton here. We're just going to do this internal lazy man's way of doing it, right? One of those groups is a good acid, one of them's a good base, so our base is going to accept the proton from our acid. Done and done. Okay. Now, if we just look at where we're going here, our destination, I guess let's put that in real quick. We got that carbon-nitrogen double bond. Notably, what atom is missing in this imine here that we started out with in our acetone? The oxygen, okay? Cool. We need to get rid of this oxygen here. We need to cut this bond right here. But we got this common problem that we've seen with alcohols over and over and over again, which is that they are not good leaving groups. And we have one strategy that we've used like 1 billion times in order to make that alcohol a good leaving group. All right, and what is that? We're going to into water, right? Turn it into water by protonating it. Awesome, okay, and again, our proton donor here, we're going to use that hydronium ion. So everybody take a second and do what should be that next step. Put in our arrows and our intermediate here to make that hydroxyl group into a good leaving group. Cool, so now I have my oxygen into this good leaving group here. In order to do that, that oxygen had to grab that proton from that hydronium ion. Okay? So now I need to kick off this leaving group here. Kick off that good leaving group water. But it needs a kick, right? It needs like this impetus to get it going here. It's not just going to go flying off and leave behind a carbocation. All right, so where does that kick come from? This is, I think, one of the more surprising steps in this mechanism, but we saw this as well with our acetyls, okay? This pair of electrons right here is going to be the one to do it. It's going to come down and kick off that leaving group. That pair of electrons, that lone pair from that nitrogen atom, is going to form a, well, I'm going to let you tell me what it forms here by drawing our intermediate. We kick off water, goodbye. What's our organic product of this step here? right, so importantly, when that pair of electrons comes down, I'm no longer going to have a carbon-nitrogen single bond. I'm going to have a carbon-nitrogen double bond. Right, to be clear, this lone pair of electrons that came down formed my new pi bond with that carbon atom. And something's wrong with my intermediate here. What's it missing? Charge. What should the charge be? Positive. It's got 4 bonds, no lone pairs anymore. So that nitrogen is positive. And look at that. We are so close to our imine product. I want you all to take the second and fill in this last missing step here to get us to that imine product. Alright, so we just look here. We have to play the spot the difference game. I got 2 nitrogens on the right-hand side and only 1 on the left-hand side, so I need to get rid of this bond right here. What do we call things that take protons away, that take hydrogens away? Bases. So I'm just going to use my base. Again, under these neutral conditions, the base that we're going to use is water. So water will accept that proton from that nitrogen, giving me my imine product. All right, so if I printed out this mechanism and just showed it to you, you would be like, oh crap, what are we looking at here? All right, this both is and is not that bad if we think about it step by step, right? So let's just go through and kind of talk about these steps again. This very first step was just a straightforward nucleophilic attack. Exactly like we would expect to see for the first step in every single nucleophilic addition reaction of aldehydes and ketones that we've talked about. All right, nucleophile attacking that electrophilic carbonyl carbon. We get this very weird neutral intermediate here where we have a positive charge on our nitrogen and a negative charge on our oxygen. So then we have to just kind of make these right again by doing a proton transfer. Okay? And then we had yet another proton transfer in this step here. And what was the purpose of that proton transfer? To create a good leaving group, right? So exactly, we got to get rid of that oxygen. We know we're going to need to kick it off at some point here. We need to turn it into a good leaving group. So we got proton transfer to make a good leaving group. All right, and again, this is kind of one of the more counterintuitive or surprising steps in our mechanism here, which is where does that impetus come from for kicking off that leaving group? Like up until now, it's always been some other nucleophile coming and attacking, and that's what kicks off a leaving group. This is coming from within the molecule itself. We got this internal rearrangement here. All right, so in this next step here, we have the lone pair of nitrogen kicking off our leaving group. All right, and then the last step, now we just have our protonated imine. So in order to get our product here, what are we going to do? Yet another proton transfer step to make our neutral product here. Cool. All right, so this mechanism both is and is not that terrifying. All right, there are a bunch of steps in here, but if we take it step by step, we can reason our way through it. All right, and again, with a primary amine, we created this weird product we call an imine that has a carbon-nitrogen double bond. All right, if we instead were to use a secondary amine, we get that enamine product. All right, and let's see if we can't reason through this. We'll start again with that simple acetone ketone here. Now we have to use a molecule that has 2 carbons bound to that nitrogen. We'll just make them methyl groups to make our lives a little bit easier. All right, so let's see if we can't reason our way through this mechanism. Again, our first step is going to be a nucleophilic attack. All right, so see if you can't get that first step in our mechanism given our substrate and our reagent here. Again, we have our nucleophilic attack on that carbonyl carbon. That pair of electrons jumps up on onto that oxygen to create a negatively charged alkoxide ion. And now we have our nitrogen stuck on there. It's got its 2 methyl groups. And then a hydrogen. And because it's got those 4 bonds and no lone pairs, it's going to have this positive charge. So again, we see this intermediate here that has both positive and negative charges. And we're like, man, that's weird. It's perfectly allowed under these neutral condition mechanisms. But again, it looks kind of weird because one of those is a proton donor and the other one is a proton acceptor. So again, our next step here is going to be a proton transfer to create that neutral intermediate. So again, our oxygen is going to steal that proton away from that nitrogen because that alkoxide ion is a good base and that positively charged nitrogen is a good acid. So now we have this neutral intermediate here. Okay? And if we look at this thing here, this is kind of what we would expect our product to be based on all the other nucleophilic addition reactions that we talked about. We have that hydroxyl group, or we have that hydroxyl group from our carbonyl oxygen, and we have our nucleophile stuck on there, right? This is kind of what we would expect based on the scheme that we've discussed up until this point. But this thing here, what I'm pretty sure is called a carbonylamine, but don't quote me on that, is unstable, right? We don't stop here. This thing continues to react further to create our enamine. And what happens is we have this proton transfer that makes that hydroxyl group into a good leaving group. Again, our proton transfer to make a good leaving group. And again, we're going to now kick off that leaving group. All right, based on analogy to what we did in our primary amine mechanism, I want everybody to take a second and kick off that leaving group for me. All right, so where does that impetus come from to kick off that good leaving group? Right, the call's coming from inside the house on this one here. It's within that molecule itself. That lone pair on that nitrogen is going to come down and kick off that water. All right, so if we were to stack these two mechanisms side by side, the one for our primary amine and the one for our secondary amine, we would see that they're literally identical up until this point. Okay? With our primary amine, the last step was pretty straightforward here. We just had to take a proton away to make it neutral again. Okay? If we look at our secondary amine, we got a problem here. These are no longer hydrogens that we can just pluck off. These are now these methyl groups. All right, you're not just going to be able to pluck those off with a base like we can a hydrogen. All right, so let's remind ourselves where we're going here is not that imine product, but that enamine product. All right, so I am again going to have to do a proton transfer here. But importantly, where is that proton going to have to come from? All right, draw in your hydrogens, your implied hydrogens on these structures here. Let's see if we can't figure this out. All right, if we look at these methyl groups on our nitrogens, we got 3 over here and 3 over here. That doesn't change. If we look at this carbon right here, we got 3 and 3. That doesn't change. All right, but now let's look at this carbon right here. We're going to color it specifically. How many hydrogens does it have on the right-hand side? 3. And how many hydrogens does it have on the left-hand side? Only 2. So where is that proton going to come from? It's going to come from that neighboring carbon, right? So instead, our last step here is still a proton transfer. But it looks a lot more like that elimination type mechanism here. All right, it's the hydrogen on that neighboring carbon that's going to have to be removed. We'll use our base to do it. All right. Now, importantly, this pair of electrons is not just going to jump onto this carbon atom. That would form a negatively charged carbanion. This pair of electrons right here is what's going to form my new pi bond. All right, so for the sake of time, let's just show it's going to come down, form that new pi bond. All right, we can't have a carbon with 5 bonds. That would be ridiculous. So what happens to that existing carbon-nitrogen pi bond? It's going to jump up onto that nitrogen atom. All right, so for our secondary amine, our steps in our mechanism are the exact same, with the exception of that last proton transfer step, which is this elimination type step to form that carbon double bond. Cool, so yes, nitrogen nucleophiles, kind of a pain in the ass, right? We're going to keep them in a separate category in our mind because they behave a little bit differently than all of our other nucleophiles. Cool. We'll finish this off next time.